Okay, so let's start from the last lecture. And so I posted a lecture regarding the remaining part of the model of a PN junction. If anybody has any questions regarding what was discussed here, we can take it up right now. Otherwise, we'll go on with analysis of use of PN junction diodes to analyze circuits. How do we go about deploying models to find the circuit parameters of interest? No questions? The other thing is, if you have any questions, you can also post it. You can send email. You can write it with hand, take a picture, send it by email, and in the next lecture we can take up those problems. Okay, let's continue then. This is the model that we had put forward for a diode in forward bias. In the forward bias condition, we said diode can be thought of as three elements: a current source here, voltage dependent current source with an exponential characteristics, and a junction capacitance or depletion capacitance here, which is also voltage dependent, and a diffusion capacitance, which is dependent on the amount of forward current which is there in your diode here. So the forward current results in a certain diffusion capacitance here. Now it turns out that the diode that you're going, so if we give you these 7 parameters, then you can use the diode in the circuit that you are trying to analyze here, because with these 7 parameters you can find out. Yes. IF depends on the current here. This current here does not depend on, for example, the current that flows here through CJ. Only this current here. Okay. Or this current that comes about, as we said, it comes about because of charges which have been injected in P and N regions. So it represents, the current represents the stored charge. Okay, so the stored charge, diffusion charge, is related to this particular current. So that's why this relationship here. Okay. So going back, we said that if we give you these 7 parameters, with these 7 parameters you have the entire model at your disposal, and you can begin to use in the circuit. You know, you can then calculate the diffusion capacitance, you can calculate the junction capacitance, you can calculate the current. There's one other thing that you have to know, is that whatever circuit we design, we normally want this circuit to work over a range of temperature. We want it to work in summer, we want it to work in winter, we want it to work in the desert, we want it to work in maybe Antarctica. So there's a range of temperatures over which we want it to work, right? So we have to know about any circuit element, how does it change with temperature? Okay. So for example, if I take this particular expression for current, in this model you can see 3 elements here, 1, 2, and 3. And let's take up this particular one, equation here, which represents the DC current flowing through the diode here. If we look at this expression, we can obviously see temperature dependence. The VT that you see here is thermal voltage KT by Q. So that's an obvious temperature dependence here. But aside from that, the saturation current, IS, that you see here, the IS is also very strongly dependent on temperature. The IS, without going into the details, IS is exponentially dependent on the band gap of the semiconductor here, EG by KT. So there is a strong dependence on temperature of the reverse saturation current also. Now if you note that there are 2 tendencies. If temperature increases, let's say I take my diode, I bias it at a fixed voltage VD. If I bias it at a fixed voltage VD, if temperature increases, then you note that VT will increase. VT will increase, which means that this term that you see here will decrease. The exponential will decrease. But what happens is, the IS actually increases. Note that IS is e to the power minus EG by KT. So IS increases. And it turns out when we look at the 2 numbers, the increase in IS is much more than the decrease in this particular factor. So actually, as the temperature increases, the diode current, if you fix the voltage here, if you fix the voltage 0.7 or 0.6 or whatever, if you fix the voltage here, the diode current would increase with temperature and would increase exponentially. We said diode in forward bias, this -1 is negligible. So note that this is exponent Vd by Vt and Is is exponent minus Eg by Kt. So it would increase exponentially with temperature. So the diode then is very, very sensitive to temperature here. Okay. On the other hand, many times what we do is we don't fix the diode voltage. It's the other way around. Many times we fix the current flowing through the diode, and then we are interested in knowing how the Vd changes here. So in that case, you can, it's the same thing. If you fix Vd, and we are saying the current increases with temperature. On the other hand, if I fix current, then you would expect that the voltage across the diode would decrease with temperature. Okay? So we can see it from here again. We can take this particular expression and rewrite it as Vd equal to Vt ln I0 by Is plus 1 here. And the first term gives an impression again. It gives a wrong impression. If I look at the first term, it gives an impression that if my I0, the current through the diode is fixed, it appears as if Vt, because Vt increases linearly with temperature, so you would expect the diode voltage to increase with temperature. But again, it's not the Vt term which is dominant, it is this Is term which is dominant here. So Is actually increases significantly with temperature, exponentially with temperature. So this term is actually reducing, and overall Vd again reduces. Okay. So a rough rule of thumb is that for silicon diodes, Vd decreases at the rate of, these things do vary from diode to diode depending on also the current at which the diode is biased. A rough rule of thumb is around -2 millivolt per degree Celsius. For every 1 degree increase in temperature, the diode voltage is going to fall by 2 millivolt. If you bias it at a fixed current. So we are assuming current is fixed, and then we are asking what is the rate at which the diode voltage falls. And it falls at this particular rate. It may look to you small, -2 millivolt, but just note the following. If let's say the diode voltage is 0.7 at 27 degrees Celsius, then at 100 degrees Celsius, it would be 0.554. So significant fall from 0.7 to 0.554. Now you may be wondering, I'm not going to get 100 degrees Celsius. I'm not going to operate my circuit at boiling point. But the point is, what does this temperature really refer to? The 100 degrees Celsius? This temperature that you see here, the temperature that enters into Vt and Is is not the ambient temperature. It's the temperature of the junction where the current is flowing. It's that particular point. Okay. So what happens is, note that your ambient temperature may be 50 degrees Celsius, let's say. The diode, the junction temperature could reach 75, 100 degrees Celsius. Because what is happening is, when you're forward biasing the diode, you're passing a lot of current. Okay? You have a lot of current. Note that there is a certain amount of voltage across the diode. So if you're passing, let's say, 1 ampere of current, just a hypothetical case, say there's a diode, you're passing 1 ampere of forward current, and the voltage across the diode is 0.7 volt. So the power which is being dissipated at this particular place is 0.7 watt. That's a lot of power, a lot of heat being generated. Where does that heat have to go? It has to go towards the ambient. The heat has to be released to the ambient. Now, so you can realize if the ambient is 50 degree and I have a source of heat and the ambient is 50 degree, the source is going to be, there's a thermal resistance between the ambient and the source of the heat. So what happens is the junction temperature can be significantly higher than the ambient temperature. So although I'm saying the ambient temperature is 50, your device inside, the junction temperature may be 100 degrees. Okay, so don't think that this is a unnatural number here. In fact, the numbers can be much higher also, 125, 150, it could reach, depending on how the diode has been constructed, how efficient it can release heat to the ambient here. All right, so that's something to keep in mind. The diode characteristics is temperature dependent. And therefore, if you bias it at a fixed current, the voltage across the diode will change, will drop. Or if you bias it at a fixed voltage here, the current across the diode would start increasing exponentially. I mean, that's really bad. I mean, there's a circuit, you apply a constant voltage across the diode, you expect 1 milliampere current to flow, and then you go at 50 degrees, you find 10 milliamperes is flowing. Right? So that's why you can see that we don't normally bias a diode at a fixed voltage. It's avoided. If you bias it at a fixed voltage, then first of all, the characteristics of the diode is so sensitive. If instead of 0.7 volt, if it is 0.71 or 0.72, the current changes a lot. So you don't bias the diode at a fixed voltage. You don't try to do that. Okay, you bias it on the other hand at a fixed current. All right, so that's something to keep in mind. What? That VT, of course, is a temperature dependent, and the saturation current increases sharply, increases exponentially with temperature. So these are the things that you have to keep in mind. So this is as far as the forward characteristics is concerned. On the reverse side, when I reverse bias a diode, what we saw was that there is a reverse current which flows. The reverse current could be a nanoampere at, let's say, 27 degrees Celsius here. The reverse current at higher voltage, 50 degrees or 75 degrees, could go into microamperes. The reverse current is also related to the saturation current, and reverse current also increases exponentially with temperature. So both these things you have to keep in mind. And although they may appear to you that these are disadvantages of a diode, that its characteristics is so temperature dependent, on the other hand, you can just reverse and say, because it's so temperature dependent, I can make a thermometer out of it. Right? So you can look at it as a strength, or you can look at it as a drawback as well. Many diodes, commercial diodes many of them are based on diodes characteristics. The fact that it is temperature dependent is used to make a thermometer here. All right, so that's as far as the diode characteristics is concerned. Let's come back to how do we use this particular model. So as an example, if we take this particular very simple circuit here, and if we want to analyze this particular diode, we just saw since this is a DC circuit here, so we have to use the DC model, and the DC model is over here. This is the DC model here. So if we want to analyze the circuit, we have to use models here. So let's try and do that. So one equation for this, so we are interested in finding, let's say, V0 or the current I flowing through it. So one equation, of course, it comes from KVL. The other is the diode equation here. And if you want to do an exact solution, then you have to solve these two equations simultaneously. What we could do is we could take V0 out. We could write V0 in terms of I and substitute it back here, and we get one single equation which is nonlinear. So when you use elements like diode or transistors, they are nonlinear elements. If you do analysis using these particular elements, you end up getting nonlinear equations here. Now, this is not a very difficult nonlinear equation. It's one single equation, but imagine that I can easily have 5-6 diodes in my circuit, couple of resistors, 5-6 diodes, and capacitors and all of that, and each diode is nonlinear element. Things can get then pretty complicated. All right. Anyway, how do you solve a nonlinear equation? A well-known method that many of you have seen before is an iterative method, right? What you do is you don't know what, for example, we are trying to solve these two equations together. I don't know what the value of V0 is. You can make a guess. You can start with a guess. Let's say V0 is 0.6 because we are talking about a voltage across the diode. We know the voltage across the diode would be where? Somewhere between 0 and 0.8 or 0.9, something around that, okay? So we could make a guess of 0.6. Once you make a guess, 0.6, well, I can put here 0.6 and I can calculate the current I. Once I get the current I can obtain from this, I can substitute the current I here, and I can obtain a revised estimate of V0, a new estimate for V0. And then we go back and plug it back into this particular equation, and we iterate. We iterate till we obtain convergence. And we would have some kind of a convergence criteria that the change in current delta I by I is less than a certain value. We find that the current is changing less than 1% or 10% or whatever, and then we obtain the value of V0 that we are seeking. Right? So this is a method, iterative method. There are various ways of implementing that method. So this is a method that, for example, a circuit simulator, a computer program which simulates circuits would use a method similar to this here. All right, let's see this method very quickly. So for example, for a circuit like this, I have 2 volt, I have 1K resistor, and the diode is here. The diode model is given here. diode model. Because it's a DC, so I'm not giving you the capacitances. The IS is given. We are looking at analysis at room temperature. So ideality factor N has been assumed to be 1. So the whole model is given. Everything else is known. So we assume 0.5. We calculate current. We substitute it back. We obtain the next guess is 0.711. So you start with the next guess 0.711. You recalculate current. You recalculate voltage. You get 0.707. Then you start with the third iteration 0.707. Recalculate current. And things are not changing. The current is within a few percentage points. So you may want to stop here and say, well, the diode voltage is 0.707. The current is 1.293. Now, good thing about this is that your guess need not be very accurate. For example, I could start with 1, right? I could start with 1 volt, this thing, and repeat it here. With 1 volt here, the next guess itself comes out to be 0.7. 0.7 here, 0.707, and we are back to the same value here, okay? But, you obviously know from your prior background in maths that there are problems with this. If you make a wrong guess, you may end up with the wrong solution also. So I'm not claiming that no matter where you start, you'll end up with the right solution, okay? So there are issues with it. But that's how the iterative method works, right? So it allows you to solve a nonlinear equation not in one pass, but in multiple passes. You're able to zone down to the result that you're looking for. Obviously, you can see here for a one diode circuit, I can do that. But for multiple diode circuits, multiple sources, this is not going to be easy. Okay? It's not going to be easy. It's not something that I can take paper and pen and work out for multiple diode circuits here. So this method, iterative method, is more suitable if you take your circuit, transform it. As I said, all circuit analysis is taking a circuit and transforming it into a set of equations. So if you have multiple diodes, transform it into a set of equations, write a computer program, which will do this for you, which will take a guess and then go through all of that. So it's ideal for a computer implementation rather than working out with paper and pen. The other method is, which is interesting, which is the graphical method. Graphical method. So we are talking about solving two equations. So I have this equation here, same circuit. Vs is IR plus V0 and I equal to Is here. These two equations are here. And I want to solve them by graphical method. So first thing what I do is I take this equation that you see here. I write it in terms of I. I equal to Vs minus V0 by R. So I write it like this. Now I have two equations. I have a diode equation I here, and I have I equal to Vs minus V0 by R. I plot both those equations here. So plot the I equal to Vs minus V0 by R. It's a straight line here. Vs by R here, Vs here. So that's the straight line here. Plot the diode. Plot the diode. Wherever the two intersect will give you the solution here. Right? So that's something also. This is called the graphical method. It's also called the method of load line. Load line because you have, aside from the diode current plot that you see here, you have drawn a line here, I equal to Vs minus V0 by R. R may be the load resistance. So this particular equation is related to the load value here. Load value here. So this is like the load line, and load line intersecting with the diode curve gives you again the solution here. Again, simple to use with one diode. Multiple diodes, the method will get you'll get into a problem. Again, so we'll work with simple cases, but for other cases, it's not so convenient here. All right. So this is an example that one can do. So earlier it used to be difficult. You have to take a graph paper and plot the two equations. Now we have very nice plotting programs. You can enter the equation, they'll plot it for you, and you can see the intersection and get the value. So it's easy to use it, but again, for multiple diodes and more complex circuit may not be very suitable here. So what we find is that for hand analysis meaning paper and pen of circuits, we need simpler model. Okay, we need simpler models, and so what we are just seeing that use of nonlinear model, although conceptually is simple, there's nothing as far as concept is concerned. There's nothing very deep about it. But working it out, solving it is difficult and time consuming. Especially, as I said, if you have more than one nonlinear elements here. Also, note that in both these methods, when I use it, I get a value, 0.12. I get a value 0.12, or in the iterative method, I get a value, whatever is the value of the current. I don't get an expression. Okay? They don't yield expressions. Now, a symbolic expression is valuable for me because just looking at the expression, it helps me understand how the circuit behaves. So, as I've said, one of the goals of analysis is not just to obtain a number, but is to understand the circuit. And understanding is facilitated if I end up getting a symbolic expression here. So, in order to get a symbolic expression and make the analysis simpler, we need simpler model of the device here. So, one of the models of diode that you're familiar with is that a diode in forward bias, we will approximate the diode by a battery with a certain value here, V gamma. And in the reverse bias, we'll approximate the diode by an open circuit. Simple model, obviously, the results that I'm going to get with these models are not going to be accurate. So we are sacrificing accuracy, but what we are gaining is simplicity of analysis, simplicity of final expression, and we'll get a symbolic expression which will help us understand how our circuit is how our circuit works here. Now, there are a little bit of if you read about it, there are misunderstandings associated with this V gamma. Okay, what are we doing actually? When we approximate the diode by a voltage like this V gamma, what is it that we are doing here? If you look at this diode in the forward bias, it's an exponential characteristics here. And what we are saying is that we are approximating it by a straight line here, and we are calling this as the V gamma. And the words that are used for this is cut-in voltage, offset voltage, and things like that. Okay, so we are saying that the diode can be described by a battery with a voltage V gamma, which we call as the cut-in voltage. Typical values that we take for it range from 0.6 to 0.7 volt. Okay, but this way, now let me illustrate to you what the misunderstanding usually comes about. How many of you have seen this book? Not many. Millman and Grable. It used to be a very prominent book. A lot of people are still reading this particular book. Let me tell you what the misunderstanding is. Let's take this particular book and read through. I've just taken a paragraph from here, from this particular book, and expanded it. If you read in this particular book, here, it says, the author is plotting the diode characteristics, showing the diode characteristics, and says a noteworthy feature of this characteristics is the existence of a cut-in, offset, or turn-on voltage V gamma, below which the current is small. V gamma is approximately 0.6. Beyond V gamma, the current increases rapidly. Beyond V gamma, the current increases rapidly. So what is being implied here? It's being implied that diode has a cut-in voltage. There is a cut-in voltage or offset voltage in a diode. Below that cut-in voltage current is very small. Above that, something different is happening above V gamma. That below V gamma, maybe something else is happening. Above V gamma, the current is rising sharply. Above V gamma, the current is rising sharply. And therefore, the diode has a threshold or a cut-in voltage, which is called V gamma. Now, this is a misconception. Why? Because there is no cut-in voltage inside a diode. Same characteristics, if you look at it, the author actually on the second page plots this characteristics on the exponential scale, on the log scale here. Same here on the log scale here. Can you see that there's anything special about 0.6 in this when you look at it? I mean, is it that beyond 0.6 the current is increasing rapidly? If I look at 0.6, below 0.6 also is exponential, is increasing rapidly. Above 0.6 also is exponential, is increasing rapidly. There's nothing unique which is happening at 0.6. Nothing unique which happens at 0.6 here. It's just a fallacy which occurs when you plot things on a linear scale. On a linear scale, if you take an exponential and plot it, it would always appear that below a certain voltage current is negligible, above a certain voltage current is significant here. It leads to a false impression that there is something called a cut-in voltage. Actually, there is no cut-in voltage inside the diode. There is no offset, no cut-in, nothing. There's nothing like that, especially when you see a exponential characteristics. So this is a very common fallacy that students carry when we ask students, in our MTech interviews and others. They will say there's a cut-in voltage. A diode has a cut-in voltage, okay, which is perhaps stemming from. There are other books as well. For example, if you take, there's another book which says, note that the current is negligibly small up to 0.6 volt and rises sharply beyond that. That is as if after 0.6 something special is happening inside the diode. That something, suddenly the current is taking off. And I just showed you, current is not taking off or anything. Current is exponential above 0.6. Current is exponential below 0.6. What is really happening is that we are just approximating. There is no cut-in voltage inside the diode. We're just taking an exponential, as I said, and we approximate it for convenience, for simplicity, and whatever is that voltage at which we approximate, we call it cut-in voltage here. A good way of removing this misconception is if I show you a plot like this, right? What is the cut-in voltage? Let's assume there's a cut-in voltage. What will be the cut-in voltage for this diode? Below which current is 0, above which the current is increasing sharply. Right? What is the cut-in voltage? 0.6. You all agree? Okay. Another diode. What is the cut-in voltage? Above which the current is increasing sharply? 0.3. All of you agree? Right? Let me put both of them together. Both of them are the same diodes. It's the same diode 1N4007. In one case, you are saying cut-in voltage is 0.6. In the other, you are saying 0.3. What is the difference? Can you see the difference between the two? The scale at which you are looking. I'm looking at a 100 milliampere scale. And on a 100 milliampere scale, if I want to approximate my exponential, I'll approximate it as cut-in voltage would appear 0.6. On a different scale, on a 0.1 milliampere scale, is 0.3. There is no cut-in voltage inside a diode. There's no unique voltage. There's nothing unique about a cut-in voltage that above it, the current increases exponentially, very sharply. Below it, it doesn't increase sharply. There's nothing like that. It all depends on the current range of interest. If you are interested in a current range of 0 to 100, well, fine, you may, if this is a current range which is of interest, you may approximate it by 0.6. If there is some other current range of interest, you'll approximate it by something else. Okay, which is what you must have seen in the homework assignment also. When we gave you a equation like I equal to V to the power 6, and we said approximate it over one current range, you got one particular value. We said approximate it over a different current range. You must have gotten a different set of values, right? So it's as simple as that. And as I said, if you plot it on the exponential log scale, you can clearly see there's nothing unique about 0.6 or any other voltage here. The current is increasing as sharply at 0.6 or as at any other place here. If you are interested in currents around 1 milliampere, if that's the range of current at which you are working, then you may approximate the diode by 0.6. If the range of current that you are interested in is, say, a microamperes, you may approximate it by 0.3. So it all depends on what range of current is of interest to you. And depending on that range of current, you approximate the diode by 0.6 or 0.5 or 0.4 or 0.3. There is no cut-in voltage inside the diode here. Okay? So keep that in mind. Now the other misconception that arises, once you think that there is something unique cut-in voltage inside a diode. Okay? Suppose you do carry the impression that there is a cut-in voltage inside a diode. This is another picture that we said that inside a PN junction at equilibrium, there is a depletion region here, and inside the PN junction, there is electric field and there is a built-in voltage. Built-in voltage exists inside a PN junction. But then, the other misconception that many times students carry is that the cut-in voltage is the built-in voltage. The cut-in voltage is, so you're carrying an impression what? You're carrying an impression in your mind that below cut-in voltage, the current is very small. Above cut-in voltage, something happens and current increases rapidly. So you're carrying that impression. Then you know that there is a, if I look at a positively charged carrier, it encounters a barrier. A hole encounters a barrier in going towards the N side. And therefore, it must be that once I remove the barrier, then the current really takes off. So once I remove the barrier, the current really takes off. And therefore, maybe, in fact, none of the books are really stating it, that the cut-in voltage is VBI. I think this extrapolation is happening in the minds of students. So they are putting 2 and 2 together. It's not being said that. So there is a concept of cut-in voltage. They know that there's something like built-in voltage exists also. And they know that built-in voltage means that the holes have a difficulty in going towards the N side and the electrons have a difficulty in going towards the P side. So therefore, if I apply a voltage which removes VBI, if I apply a voltage V equal to VBI forward bias, then there will be no barrier and then the current would suddenly increase significantly. And therefore, the cut-in voltage must be built-in voltage. The cut-in voltage is not built-in voltage. As I just showed you, cut-in voltage is only approximating the diode's characteristics in a certain current range. It could be 0.6, 0.5 or whatever. It's less than VBI. Okay. So very important phrase. Learning is not just accumulation of knowledge, but detection and correction of errors as well. Okay. So keep that in mind. All of us carry, when we learn something, don't think that we learn as it is. There are a lot of misconceptions that we are carrying. It's important to detect those and correct those here. So this is one of them. All right. Okay. So what we are saying is that yes, it's very convenient to approximate the diode by a battery, right? But note that if you approximate it by a battery, please be clear that if the voltage that is there along with this particular battery here, that has to be significantly larger than this for the model to work properly. Right? So for example, if I approximate it by a battery, the current is I equal to V minus VD by R. Any error in current coming about because of error in the diode voltage would be delta I will be equal to minus delta VD by R. Percentage change in current is delta VD by V minus VD. What is delta VD? An error that I've made. So I've approximated the diode by 0.7 volt, while the actual diode voltage may not be 0.7. We know that diode voltage varies with current. So actual diode voltage may be something else. So as a result of this error, how much is the error in current that I calculate? And that depends on, as you can see here, depends on the error, but depends on this voltage here, V. V is nothing but Vs here. Depends on this voltage V. So if, for example, as you can obviously see, if Vs approaches Vd, then my constant voltage approximation becomes very poor. For example, for this particular circuit, if I evaluate it at 1.7 volt, if I take Vs equal to 1.7 volt and do the analysis, I get a certain value of current, and accurate analysis gives me a certain other value of current, and the error is 9%. On the other hand, when I make Vs as 0.8 volt, now note that this Vs is 0.8 and the Vd is very close to it, so the errors are large, the errors become 63%. Okay, so when you are using this constant voltage model, please be clear that the voltage attached to it is sufficiently large as compared to this value. If it's sufficiently large, your results are going to be reasonable. But if it's very close, the results are going to be highly erroneous. So this is another one of our standard interview questions. So we give a circuit like this and we ask a student to give us the value of current. Right? So very easy. Everybody goes and puts a 0.7 volt battery. So 1.7 minus 0.7 divided by 1K, so 1 milliampere. Right? What is the next question which comes after that? Right? This is the next question which comes after that. Fine. So we apply 0.7 volt. What is the current? So typical answer that comes 0. Typical answer that will come is current is 0. Well, the first thing is that's what is important. What am I saying? I'm saying when the voltage which is attached is sufficiently large compared to this, your model is okay. You can't apply your model now. 0.7 you can't. It's no longer valid. When the voltage attached to this particular one is 0.7 itself, the model is no longer valid. Every model, remember, is an approximation. It has a range of validity. Now you start using this particular model here with 0.7 volt source and you put 0.7 volt here, obviously you're going to get the wrong answer. You're using it at the wrong place. And so that's what I've been cautioning you, that yes, we learn a model and we forget where to use that particular model. We start deploying it everywhere. And in this case, if we start deploying it, we get a wrong answer. We can't assume it to be a 0.7 here. And when I share these slides, please work it out. What is the correct value of diode current here? Okay, in this case. All right. So a better model of a diode is not just a battery, but you approximate it by a little bit better, which is add a resistor also to it. And in the reverse bias case, we keep it as open circuit. Or if you want to make it a little bit better, you can approximate it by a reverse saturation current. 1 nanoamperes, 10 nanoamperes, whatever it is, you can approximate by a current source. Okay. Now, where is this model coming from? Well, so here is the diode characteristics, and I'm approximating it not by a vertical line. We've already preempted this particular discussion in our homework assignment. Remember, we approximated by a straight line rather than a vertical line, a line with a slope here. So here is the diode characteristics. We approximated by, there are different ways of approximating. This approximation is with a V gamma and a slope here. So when we approximate our exponential characteristics by a piecewise linear approximation, piecewise linear means till here we say current is 0, and then we approximate it by a line of a certain slope here, and the slope is basically the resistor value here. So that's where this particular model is coming from. We are taking our exponential characteristics, approximating it by a two-piece segment here. One segment till here, and the other segment is till here. And the slope is what is giving rise to the R here. Now, there's another misconception associated with it. And the misconception is that this R that you see here in series with it. So as I said, the first misconception is that the cut-in voltage refers to the voltage across the depletion region. It's like the built-in voltage. And this R that you see here is an R which is inside the in these regions here. Now, it's true that when you take an N-type semiconductor and a P-type semiconductor, N-type has a certain resistance, P-type has a certain resistance. But those resistances are not what we found here. These are not the resistances of N region and P region. All that we are saying is it's an exponential characteristic which we are approximating by a line with a certain slope. That's all. It's not referring to the resistance of the N region or the resistance of the P region. Again, you can see it if I let's say if I take my exponential over a current range of from 0 to 0.05 and I approximate it, and we get an approximation. V gamma is 0.75. The resistance has 1.4 ohms. Right? It's an approximation. If I approximate it over a different current range, I get a value V gamma 0.63 and a resistance of 150 ohm. Right? So it's not really the resistance of the N region or the P region. Again, it's simply taking an exponential and approximating it. Depending on the current range, I may get different values of V gamma. I get a different value of RF here. Minor points, which is basically that we have seen that for a diode, and that's true for any element, we can build a range of models here. We saw a model like this here, more accurate model with an exponential characteristics, with a capacitor here, junction capacitance and diffusion capacitance here. For DC, we saw that you could, instead of taking an exponential, you could approximate it by a battery and a resistor and an open circuit here. If you want an even simpler model, you approximate it by simply a battery. If you want even simpler, well, in forward bias, you just say it's a short, and in reverse bias, you just say it's an open. Right? So we have a range of models starting from simple to more complex, and obviously the accuracy is going to increase in this particular direction here. The accuracy of the results that you get is in this particular direction, simplicity is over here. Now, all these models are useful. All of them are useful. For example, in this case, when I'm approximating the diode by a short, if I'm looking at, that diodes are used as in power supply, in rectifiers and power supplies, right? In a power supply, the input voltage is 220 volt, right? The input is 220 volt, and the diode voltage is 0.7. 0.7 with respect to 220, you'll say, well, let me neglect it. So in forward bias, you can just consider a diode to be a short. It may not be a bad approximation when I'm looking at 220 volt, when I'm rectifying 220 volt. On the other hand, when I'm rectifying a smaller voltage, then maybe V gamma is enough. And then, there are places where you may find that you need to take this particular model into account. And of course, if you're looking at the most accurate answer, then you use the exponential diode characteristics. By the way, will you get the most accurate answer if you use this? Or you can get even more accurate answers? The most accurate answer you'll get by actually building it, right? By actually building the circuit. So you take a diode and you actually build it, and then you'll get the most accurate value. Because remember, all these models are again approximations. When you read a data sheet, I would suggest that, for example, there's a diode called 1N4148, or there are many kinds of diodes. If you just go on internet and you read a data sheet of a particular diode. Now, when you read the data sheet of a particular diode, you will see the manufacturer would give you some values here. Let's take IS for an example. IS, reverse saturation current. The manufacturer may give you IS is, let's say, 1 picoampere. But you would also see in the data sheet that there is a typical value, there is a minimum value, and there's a maximum value. So this IS that you see here, the manufacturer may be saying is 1 picoampere, but this IS value varies from diode to diode. We don't have enough control over our fabrication that all the diodes which are produced will have 1 picoamperes of saturation current. The diode that you take in the lab may not have 1 picoamperes. It may have 5 picoamperes. Okay. So if you're thinking that I'm going to analyze my circuit, and the answer that I will get from here will be exactly the same as the answer that I will get by actually fabricating it, the answer is no. Every model is an approximation. In fact, in this model, there are lots of approximations which we have not told you. For example, I said ideality factor n, right? Ideality factor n, I said it can be 1 or 2. Ideality factor is a function of bias. At low bias, the ideality factor may be 2. But as you go towards higher bias, the ideality factor may be 1. So there are more complications. Don't think that this is the most accurate model also. There are more complications that are there. And but as the model becomes more accurate, it becomes more complex. And maybe in the next lecture or so, we'll look at when we want to do very accurate analysis, you go to circuit simulators. So we'll introduce you to a circuit simulation and then see how these models can be used. Okay, so let's stop here.